Alright, this is Mr. Heebner. We are continuing with part 2 of bonding notes, looking at the Born-Haber. Alright, so we're in the Born-Haber notes. We're continuing from yesterday. And just to recap, what did we do? We were looking at, the heat of formation. Lithium plus fluorine gas forms lithium fluoride. And here's the heat of formation. It's an exothermic process. But all of the steps leading up to it, we can utilize to figure out ultimately the lattice enthalpy energy of this system. So first thing is you got to sublime the metal to make it a gas. You got to have two gases come together. You can't have a solid and a gas if you're talking about the lattice enthalpy energy. And 161, that's going to be given to you. You don't have to do any work for that. However, for the ionization energy, now that you got a gaseous lithium, you ionize it, and that is found on page 8 of your data booklet in the little periodic table. 520 is the value that we got. And then we're going to take the fluorine gas, and we just need one fluorine, not two of them. So we take the half of the bond enthalpy energy of fluorine, which we found was 79.5 kilojoules per mole, and this is on page 11 that we found that of the data booklet. Then we got to do the same thing with fluorine, ionize it by doing the. Oh my gosh! Sorry guys. Thanks for letting me know. I got to share this thing. You guys weren't seeing anything.
We can see it. Why do they need to?
Oh, we got some chats. What's in the chat here? Yes, I was supposed to be sharing my screen. Sorry about that. I was just so excited about Born-Haber, I skipped some things. All right, there it is. It was just recapping yesterday. So we got the electron affinity, which we found on page 8 of fluorine, -328. All right, now the new stuff. Continuing on, formation of solid lithium fluoride is in the solid phase from the gas phases of each ion lattice. Okay, so we want to find the lattice enthalpy. So basically we can bring it all together then, because together these should add to form the heat of formation. So the heat of formation we said was 617 at the top, and I'm just reminding you it's -617. Alright, so let's just do it where we have some space, like on the bottom here. -617 kilojoules per mole. And this equals everything else. That includes delta H of our lattice enthalpy, which is our X, our unknown, because that's ultimately what we want to find. And let's just go backwards. We got -328. Technically, write kilojoules per mole. This is just, well, yeah. All right, this is an example. Let's write that. And then we want to add 79.5. So all of them are kilojoules per mole. I ran out of space, so I'm going to. Sorry, it's sloppy. Positive 520 kilojoules per mole plus 161 positive kilojoules per mole. All right, so essentially I'm going to take -617 minus. Actually add both sides 328, minus both sides 79.5, minus both sides 520, minus both sides 161. So -617 plus 328 minus 79.5 minus 520 minus 161. And I'm getting -1049.5 as my delta H of the lattice enthalpy. And the unit's probably what? Kilojoules per mole. Now looking at that, in the data booklet, I think it was what, page, I don't know, page, not 11, page 16 of the data booklet shows we're dealing with lithium and fluorine. It's 1049. Hey, look at that. That looks pretty good, 1049. But wait, why did we get negative and they have positive?
Oh no.
Isn't that like what it's supposed to? Isn't it supposed to be opposite?
It's supposed to be opposite, yeah. So, because these, if we look at, what are they talking about? Okay, in which the gaseous ions of a crystal are separated. So they're pulling it apart. You got to input energy to do that, so it's positive value. What this is talking about is when you put them together, it's negative value. So don't let that kind of confuse you. We are correct when we said negative 1049.5.
So why does IB want us to do this if it's like in the booklet?
So these are the accepted values, well, of the experimental values.
So they want us to find the experimental, basically?
Basically, yeah. This is the process of finding the experimental.
Okay.
Otherwise,
so if I wrote down that on my paper, they would just
no, because you'd get 0 points, because the question would be utilizing, the Born-Haber process and showing your steps. They would want all of it.
Was that better before? Yeah.
Yeah.
Oh. I never paid attention.
Do you just have to stand in that bucket?
No, that's for cleaning it out. So the chemistry students back, they wanted to see how the shower works. And
Can I do it?
I kind of want to see it.
all right, well let's pause this. All right, so bond enthalpy is energy within the bond. Where did I have this? Let's get the technical definition. I pretty much said it. Energy within the bond. And bond enthalpy can be used in heat of reaction equations and heat of formation, which we saw the bond enthalpy of fluorine in the last problem. All right, delta H equals energy required to break bonds minus energy released when bonds are formed. You can also look at it as sum of the total bonds broken minus sum of the total bonds formed. So sum of the total bonds broken, is that reactants or products? Reactants. So you can kind of think of it in terms of reactants minus products. Ooh, we got a question.
Yeah.
I think so.
I like how he's taking it right now.
Deal with it, Tommy.
Okay.
What do I do? It only lets me do the first one. I can't do number 2 or 3.
Hebrew, that's the one I told you about.
Oh. Yeah, just put it in the second question, or just submit the answers to me via email.
Alright, sounds good.
No problem. All right, so doing this example, we got to do the reactant bonds minus the product bonds. So in our data booklet, we got to look, I think it was on page 10, it looks like. Or no, those are bond length. Okay, bond enthalpy. So it's page 11 in the data booklet. So we're going to write page 11. We got C2H2. This is where we need to know how to make those molecular shapes, because we need to know how many bonds are present. So C, we got something like this. All right.
Wait, yes, there's
Oh my gosh. Oh, what am I doing? So that's a triple bond, right? Alright. And then O2. Reacts to form CO2 plus H2O. And you don't have to write all that out. This is just to help you visualize it. You can visualize in your head, that's fine. So then I've got two CH bonds. So a CH bond is C with an H. Looks like 414. But I got two of those, so it's going to be 2 times 414 plus my triple carbon-carbon bond, which is 839. And this is all on page 11. And there's just one of those. And then plus my O2, which looks like I got 5 halves of them. So I'm going to do 5 halves of my O2. Where is it? OO double bond, 498. Put this in those elbow brackets. And I'm doing reactants minus products. So CO2, I got 2 C double bonded to O bonds. That's an 804. There's 2 of them. And then I've got, oh no, I don't have 2 of those. I've got 2 CO2s. So let's visualize that. I've got 1, 2, 3, 4 of them. Plus H2O, looks like I just got 1 of them. Oh, but I've got 2 OH bonds. OH. Oxygen, hydrogen 463. Hydrogen 463. Alright, so then it's just, I think you call this algebra, it might just be arithmetic. 2 times 4, 14. 828. $29.12 I'm getting. Subtracting it by 804 times 4. It's 3216. 4142. Alright, so it's going to be negative. You got it. 2912 minus 4142. Negative 1230. And my units are probably going to be kilojoules per mole, because that's what all my values were. And we know that this is endo or exothermic? Exothermic, because it's negative. And that makes sense because this is a, what type of reaction? Combustion, because you got O2 as a reactant, water as a product. Yeah. So the 5/2 just came from the balance equation. Right there. Yeah, so you got to add the coefficients. That's how we got 4 of these double bonded CO bonds, because there's 2 times 2 of them. So. Alright, so that's bond enthalpy. That's just another way of essentially finding the delta H. As far as we got there.
Why?
Aren't you being tall with me?
My spine's in my What do you think your spine is?
I understand. I just, like, when people grow, you think, like, oh, they need new clothes. Like, their legs grow. Like, obviously,
Are you
in your
technically,
case-
this probably is also a stupid question, but are you sorry.
Alright, I want to talk about hybridization, but there's only 7 minutes, and that's not enough time to really get into it. So we got enough time to try out on the previous page this example. Perfect. I wanted to make sure that we got through bond enthalpy. That's why we kind of skipped over this. So try this out. I'll pause the video.